you, Remy, for the introduction, and thank you for the invitation to be here today. So, in the past few years, our group has been developing WIFF, the Water Information and Forecasting Framework. WIFF is a platform to provide forecasts of estuarine and coastal dynamics, and at its root, in general, it uses the EB forecasts. So, in this presentation, I want to give you an overview of our system and also to share with you our experience in using EB forecasts for our system. So, here's an outline of my presentation. I will start with a general description of WIFF. Then I'll go into a little bit more detail through an example, a platform for management of oil spill risks in the Aveiro Lagoon. And finally, I'll close with a brief assessment of using the IB forecasts in our case. So WIFF, as I said, provides forecasts of estuarine and coastal processes. I'm talking about hydrodynamics, wave propagation and generation, water quality and water quality and ecosystem dynamics, and in one particular case, we were also forecasting urban drainage. In general, our focus is in local scale, so estuaries and coastal lagoons. However, occasionally we do have to go out in the open ocean. So, for instance, we are also forecasting waves at the basin scale, so at the scale of the whole North Atlantic. But really, our interest and our focus is in the local scales. So, in very general terms, this is how each of our application works. We start by going to the internet and getting the forcings that we need for our models. I'm talking about atmospheric forcings, oceanic forcings, and riverine forcings. And this is where the EB forecasts come in, since usually we use the EB forecasts for our ocean boundary conditions. Then we run our own forecasts using previously calibrated and validated models. We compare our data with our model results with whatever near real-time data is available. And finally, we generate a bunch of products which are the ones that we provide to our end users, and normally consist of WebGIS layers, since it's through the WebGIS that we convey our results. So this is a very general overview of each of these applications, but each time we apply WIFF to a particular case, we have to tailor it to the particular needs and desires of the end users. So I'm going to illustrate this general concept now in a particular case, which is a platform for oil spill risk management in the Aveiro Lagoon. So this platform had two different goals. First, it was meant to support emergency response in case of a spill accident, and secondly, it's also meant to support planning activities from the harbor. So at the beginning, we have hydrodynamic simulation, so we have a 3D baroclinic model running every day that provides fields of salinities, temperatures, velocities, and sea surface elevations. So here you see an example of our products, which is a map of salinities at the surface. This system has some particular capabilities, like for instance, we are able to probe the model results. That's what you see here. So you basically, the user picks a point and he can extract a time series of elevations, salinities, or whatever he wants. We also use the same interface to look at data. So in this case, we have two stations, which are represented here by the red circles, and all the data that we measure is archived in a database. So the user can probe this database, extract the data. It can compare the data with the model results here in blue. Also, since this is a database, we can go back in time and look at older data if we want. Now, this is a platform for oil spill risks. So, of course, we are doing oil spill forecasts as well. So we asked the harbor administration, the end users, to pick the locations where they think that oil spills are most likely to occur. And these are the 6 locations that you can see in this figure here. So every day we run forecasts of potential spills that could occur at any one of these locations. Now, the model that we use to do these forecasts is a very detailed model, both in terms of resolution and also in terms of the physical processes that are represented. As a result, it's also a fairly costly model from a computational viewpoint. So in case of a spill, we have an alternative model. We have a particle tracking model, which is much faster and provides results in a couple of minutes. So if there is a spill, the user can launch his own simulation by using the interface where he selects the point, the location of the spill, the amount of the spill, and the time of the spill. And in a couple of minutes, he's going to have a simulation of the fate of the oil spill. Now, this is a portal not only for forecasting but also for risk management. So we have a lot of information, of layers of information on vulnerability, as you see here, and also on the risk and on the hazards. So when doing the planning, the user has access through the same portal to a lot of information besides only the forecasts. So we can combine this information of vulnerability, for instance, with the forecasts to see which are the vulnerable areas which will be affected by a particular spill. So very briefly, this is what our system looks like for the particular case of oil spills. Now, in the next few slides, I'm going to give you an overview of our experience with using the EB forecasts. Well, the first thing that I want to say is that it's very simple. It's very simple to use. With a single command line, you can obtain all the data that you need. This can be automated, so that's really a nice feature. The second important thing is reliability. For us, reliability is extremely important. If EB fails, all our system fails, and this is not just a nuisance. It costs a lot of time and human effort to put the system back online. I must say that when we started using the EB forecasts at the time of MyOcean, reliability was an issue for us. There were quite a few failures, in particular during the weekends, which was even worse. But in the past year or so, or even more than that, we haven't had any problems with reliability. I'm not sure why this happens. There are two possible reasons. One is that the EB forecasts are really more reliable, and I'm sure that that is the case. Also, we have implemented some features in our own system to survive problems with the EB forecasts. So even if the EB forecasts fail for a full day or 2 days, our system still works. So maybe that's also one reason why we haven't had problems in the past year or so. The first issue is accuracy. So, as I said, we've been using the EB forecasts, but recently we have developed our own forecast system at a regional scale. We use a different model. The domains are very similar, so this is our domain and this is the EB domain. Our model is being run in 2D barotropic mode because we are really interested in extreme water levels. And we also use an unstructured grid instead of the structured grid used by NEMO, by the EB forecasts. This means that we can concentrate our resources in our particular area of interest, which is the Portuguese coast. So we have a very high resolution, about 250 meters in the Portuguese coast, and then a much coarser resolution elsewhere. So our system has been up and running since March this year, and in July we made an assessment of our system and we compared it to the EB forecasts. These are the results. So you can see here the root mean square errors at a bunch of stations for our model in black and the EB forecasts in red. The stations here run from south to the north. So we have Las Palmas in the Canary Islands, Huelva in the south of Spain, and 4 Portuguese stations, several stations in Spain, and the last 2 stations are in southern France. So by and large, what you can see is that the errors are not awfully different between the 2 models. However, there are still some differences. In general, our model is more accurate in the southern part of the domain, in particular in the Portuguese coast, and the EB forecasts are more accurate in the northern part of the domain. So we attribute this difference to the fact that our model is very fine in the Portuguese coast and then it becomes coarser elsewhere. There is also a notable exception, which is Port Bloc. where our model is actually better than the day before forecast, contrary to the other stations in the same region. We believe the reason for this is that Port-Bloch is located at the mouth of the Gironde estuary. The Gironde is a very large estuary, so it probably affects the water elevations. Because we have an unstructured grid, we can represent part of the Gironde, which may not be the case for the EB forecasts. So what this suggests is that refining the model, refining the grid would probably improve the results of the EB forecasts. So how can these EB forecasts be improved? Well, first, the results that I just showed suggest that the accuracy could be improved by refining the grid. I'm not saying that the accuracy is not good enough. It's certainly very good, but there's certainly room for improvement. Secondly, it would be very nice for us to get the output with a finer time step. So we are getting the sea surface elevations with a 1 hour time step, and the other variables are daily averages. What we do with the sea surface elevations is that we use cubic splines to interpolate in time between 2 consecutive hourly time steps, and this seems a bit silly since the model certainly has a finer time step. For the other variables, salinity and temperature, using daily averages certainly makes us miss part of the daily variability of the salinity and temperature, which is a pity. And the third issue would be providing a spatial interpolator. So what we get from the EB service, from the Copernicus service, is a subgrid, so a chunk of their grid, and we have to interpolate both in the horizontal and in the vertical to get the information that we need. If we could get directly the information that we need at the points where we need them, this would save bandwidth, and it would save a lot of disk space since we end up archiving all this information. So in one of the presentations this morning, you could see that the number of terabytes that are downloaded from Copernicus every year is really enormous, and I think we could reduce this number by providing a spatial interpolator, so giving us only the data that we need rather than forcing us to do the interpolation. And these were the suggestions that I had. I'd like to thank you for your attention. Thank you.